We are Team Zebra Blitz, and our project is energy harvesting to power a patient tracking Bluetooth angle of arrival locator. We are led by Timothy Vermilia, the systems engineer, Dave Teal, the principal software engineer, and Mike Smith, our consulting technical director. The URI team includes myself, Fatima Lynch-Smith, an electrical engineer, Alexis Estrada, a computer engineer, and Kashmir Ryan, also an electrical engineer. Our sponsoring company is Zebra Technologies, and they are headquartered here in Lincoln, Rhode Island. Zebra is a company that provides a wide range of products and services across retail, healthcare, and transportation and logistics and other industries. These technologies are used to intelligently connect people, assets, and data. There are currently patient tracking systems available on the market. However, these systems are expensive and take excessive amounts of time to install due to the wired design. They also continuously draw energy from the power grid, raising electricity costs. The Blitz locator is a device that will be scattered throughout a hospital environment and use complex angle of arrival algorithms to track patients wearing wristbands. Our project revolves around designing a Blitz locator that will track patients in various healthcare settings with 99% accuracy. These devices will reduce the cost of materials and labor and will be installed in under 2 minutes without any wiring. With this block diagram, you can see that the Blitz angle of arrival wristband beacon communicates with the Bluetooth locator. These locators are able to communicate with each other. The data is sent through a location engine with filtering. After this process is complete, the data is visible through patient flow analytics and can provide real-time alerts for the end user. The Blitz locator will be powered by ambient lighting using photovoltaic cells to harvest low light in minimal conditions. A PV cell is a semiconductor material, usually silicone, that is used to collect light energy and convert it into electricity. When talking about low light levels, such as indoor light, a measurement known as lux is used to measure the light intensity. The anticipated best outcome of this project was to conduct rigorous research and analysis of cutting-edge photovoltaic technology and select our top 2 vendors for the Blitz locator system. We were able to achieve our anticipated best outcome by researching PV cell types and conducting tests to determine performance, efficiency, and optimal configuration. Our team has made several accomplishments across the fall and spring semesters that led us to meeting and even exceeding our anticipated best outcome. We thoroughly researched PV cells and then honed in on specific manufacturers. Influenced by the locator's intended use and environment, we developed a test method to test fixtures to conduct scent testing. We conducted several tests with samples we acquired from manufacturers and analyzed this data to determine the top 2 contenders. We even went as far as designing the potential prototype housing depending on the results of our testing. My work consisted of collecting data from specification sheets from various indoor photovoltaic cell manufacturers. I then contacted those manufacturers for development kits so that we could test their compatibility with our design. Along with my team members, I also conducted several tests with PV cells and analyzed that data. In the initial phase of this project, data acquisition was vital. I researched the photovoltaic industry, specifically indoor photovoltaics, and then compiled metrics for every potentially compatible PV cell, casting a wide net. I then contacted manufacturers and ordered development kits and samples to conduct testing. I also developed a method for modeling photovoltaic cells using LT-Spice. We tested PV cell performance under various light sources to determine if the varying wavelengths affected the cell's performance. As you can see here, there is a negligible difference between fluorescent, incandescent, and LED light. After all tests were completed, we analyzed the data and found that our top 2 contenders significantly outperformed the other cells. Along with pricing information, we made a recommendation to Zebra. Our next presenter, Alexis Estrada, will explain in more detail the testing process we used.
Thank you, Fatima. Now that we have an understanding of the project and we have a glimpse of our results, you may be wondering what some of the steps required were to achieve this. We first acquired a multitude of PV cells, but we needed to determine how to measure their performance and efficiency. I designed a basic circuit that essentially harvests the light energy from a desired source and transfers the energy into a storage element, such as a capacitor or battery. In addition to designing the circuit, we opted to use a third-party program to measure the flow of energy from the source to the storage device by probing over one of the components. Here is an overview of the circuit, and as you can see, it's very simple but effective. We will later discuss our test methods in more detail. Before we could begin testing the efficiency of the PV cells, we first needed to understand the environment that the Blitz locator would be operating in. In our case, it's a hospital setting. So I dove into the regulations and standards provided by various private, public, and voluntary initiatives. There are many types of rooms in a hospital, each requiring special attention to its lighting design. For example, operating rooms must be heavily illuminated versus a patient ward, which can be very dim in comparison. Lighting in these buildings is essential to healthcare workers because it is crucial for them to be able to see clearly when working directly with patients. After gathering this information, it was time to take a trip to a local hospital and gather live data. But before we could do that, we needed the proper tools. A lux meter is required to measure lighting. There are many types of light meters on the market, some of which are handheld and others surface mounted. Additionally, certain lux meters have limited ranges, so we needed to carefully choose which meters could handle ambient lighting. We chose two, both a handheld and a surface mounted meter to gather data. The handheld meter was used to quickly locate an optimal location to take measurements, and the surface mounted device was used to collect data over an extended period of time. With these tools, we were able to establish a baseline for testing our PV cells under controlled lighting that simulates the conditions in a hospital. Between all of the data collected in our research and the testing performed, I designed two conceptual prototypes of the Blitz locator. The first is a four-sided, ceiling-mounted prototype that has PV cells installed on all surfaces. The surfaces are angled in such a way that it allows the absorption of light in the most optimal range possible and can be placed directly under light fixtures for maximum harvesting. The second is a wall-mounted fixture that can be placed in locations that may not be suitable for ceiling-mounted fixtures and can aid in covering more ground throughout the hospital. With these conceptual designs and data, Zebra will be able to optimize the Blitz locator's final design. Our next presenter, Casimir Ryan, will now be taking over.
Thank you, Alex. As you can tell, our group had a lot of overlapping components, and I hope to bring that all together for you now. Where I spent a considerable amount of my time was not only creating the test fixtures, but coming up with a method on how to implement them into our test process. As you can see here, the first test housing we created was nicknamed the Solar Simulator. The idea here is quite simple. A black 3D printed box to minimize light bleed, a light bulb socket, and a voltage regulator to control the brightness of the bulb in the housing. But how do we actually use this to conduct our tests? First, we took one of our light meters and stuck it inside of the box, closed it up, and then adjusted the bulb's brightness ranging from 50 to 1000 lux in increments of 100. Once the lux level was set, we took out the lux meter and inserted a panel that was hooked up to the circuit that Alex previously showed, and began our tests. This ultimately yielded the data that Fatima also previously showed. However, these photovoltaic cells aren't efficient if they aren't placed at the correct angle. And as you saw at the beginning of the presentation, along with Alex's designs, most of these units will be mounted on the ceiling. This is where our PV angler comes into play. We tested in the range of 25 to 50 degrees in increments of 5 at 3 different lux levels, those being 100, 500, and 1000. Using the same circuit setup as the solar simulator, the 6 different fixtures were then placed on the ceiling using a magnet. Once all of these tests were run, we were able to find out our optimal angle for the locator device. The final test we ran was seeing how different bulbs can affect the cells. In order to do so, we strayed away from just using LED lights and tested fluorescent along with incandescent bulbs. Upon research on the topic, we found that cells only care about two things: lux level and that the light falls within the visible spectrum. Since all three bulbs do fall within the visible spectrum, we were not surprised to see that there were negligible differences in efficiencies while using these bulbs. If the application called for something like UV light, these tests would definitely yield different results. Once these 3 tests were complete, we had successfully achieved our ABO, where we had completed our research, tests, data analysis, along with providing Zebra a comprehensive report on how we reached our conclusion of the top 2 manufacturers. With reaching our ABO, we can look to the future on what this could mean for Zebra. They are now one step closer to having the only turnkey solution in an emerging market that excludes the extensive installation period and maintenance costs that their competitors currently require. From an energy efficiency standpoint, we will be taking pre-existing units off of the power grid, which in the grand scheme of things isn't very significant, but is one step closer to a greener planet. All around, this concludes our presentation, and we thank you for your time.